Shaswan. Today we will talk about another topic of analog electronics. Now in analog communication, the last topic which we have already discussed, the PAM, the pulse amplitude modulation, the PDM, that's there is PDM, there is PPM, pulse position modulation, and there is PWM. PWM stands for pulse width modulation. Now, all those methods were the analog methods of communication. Whenever we were talking about analog methods of communication, there was always a problem with the signal. Whenever we are transmitting a signal, whether we need to have a synchronization like in PPM, or there was a noise levels were up like in PAM. So we were always having this problem in analog systems. So what is the best solution for them? The best solution for any kind of system, communication system, is we design a system where we convert an analog signal that is voice, electrical signal, to a particular digital signal. Now whenever we are talking about digital signal, this digital signal will always contains a better information. It always have the advantage over the analog system. And what are those advantages? In analog system, as we know, that the amplitude of that particular pulse was varied, their width was varied, and their position was varied. So there are three things which were already there. We need to use corrector so that we actually limit that particular amplitude, or we can use a particular circuit where the position of particular pulse has been determined, and you can get the better signal. But if we convert that signal, the initial signal, modulating signal, to a digital signal means the levels of that particular signal will be described in a manner where we can identify certain levels where above level is defined and lower level is defined. By this we can actually make a better component and better reception at receiver side. Now what is the advantage? What are the advantages of this digital system? Whenever we are talking about the advantage of this digital system, there are certain advantages. I have already put it over there. Now in analog systems, yes, there is a noise out there, but they were actually easy to make. But they were not flexible enough. If you want to change in the particular analog system, you have to make larger changes, and those changes are expensive. But if you are talking about digital system, then digital system always has this ruggedness to channel noise and external interference. As we know that all kind of analog systems will have this problem. These analog systems will have this problem that there will always be external noise component. The noise of the signal corresponding to particular wired network or the wireless network. In FM, it is a wireless network. In normal wired system, telephone wired system, it is a wired system. Despite that, there is always a noise interference. That electrical interference is there, the thermal noise is there, and the white noise will always be there. So what is the best way? So digital signal or digital signal system will always have this ruggedness to channel noise as well as this external interference. It will always oppose that, and you will have a better signal reception at receiver side. And it is easy to decode this signal rather than understand that signal, because if noise is prevalent in that particular channel, so that signal's SN ratio will be decreased and you will not get proper signal at the reception. The second thing is the flexible operation. Now how flexible you can make any system? As we know, in analog systems, the frequency in which it is working is always on the higher side. So it cannot be made flexible enough. But in digital system, it can be made flexible. And as you know that every component is actually designed for digital signals. It is a pulses which is discrete in level. So these pulses can be made flexible enough to cope up with other channel or other systems too. So we can design a different system on this particular system, or different systems, particular properties can be incorporated in that particular system. So digital systems are always flexible in terms of their operations. But last and the most important part in this, is the security. As we know, the analog signal cannot be made particularly secured enough that other people cannot understand it, because there is a possibility that the multiple receivers are there. It was felt during Second World War and initial phases of communications, where these analog signals were used quite frequently. And when these signals in the First World War, they were used quite frequently. In the Second World War, the better technology came, and afterwards we have been using this digital signal encryption is there. But that technology was not enough to encrypt that particular signal. So analog signals and analog systems will always have this problem. They always has this problem that this distortion and this security cannot be actually maintained thoroughly. So what we can do is we can convert them to digital signal. Now we have already studied PAM, that is pulse amplitude modulation. Now whenever we are talking about the PAM signal, pulse amplitude modulation, so in this the time is in digital form and the pulse parameters vary. Now what are those pulse parameters? The pulse parameters are amplitude, the width, which we call duration, and their position. So three parameters which were changed, but the time was in digital form in the PAM signal. So information transmission was always in analog form. It was earlier analog signals which were used quite frequently, but due to security concerns, due to their inflexible operability and their lesser immunity towards external interference and noise, was the reason we had to go for digital. Now how it is, digital signal is different from this signal. In digital signal, when we are talking about pulse digital modulation, the time and pulse parameters is in discrete form, and first time and pulse parameters were in discrete form, and then they were in digital form. They were converted in a digital form. So any analog signal which will be converted into analog digital signal will be used for pulse digital modulation. Now this signal has been used and this signal has been actually transmitted over a system. What is that system? The system itself is called pulse code modulation system. Now pulse code modulation is a system where we use a different circuit, and that particular circuit will actually gives us the chance to change the parameters, to change the analog signal into the digital signal. Now this digital signal can be sent over the channel, and then we can have the better security, better flexibility and immunity towards noise. So I will talk about the PCM. Now to start with this pulse code modulation system, we need to understand one thing, that is quantization. Now quantization is the first process to convert any analog signal into digital signal. Now whenever we are talking about analog signal will have multiple variations in terms of amplitude, and at various time intervals its amplitude will increase or decrease according to that situation. Now as you can see, this is the normal signal, analog signal, and this signal needs to be converted into a digital signal. So what is the process to do so? So what we do is, first we decide particular time intervals at which we will take the amplitude of that particular signal. Here is the time. Now at t0 time, let us suppose we will start with this point. Now the next time is, let me come again. this time interval will remain the same throughout the process. So the difference between T0 and T1 will be the difference between T1 and T2. So time duration will remain the same. What we need to do is, we need to take a particular point at which this particular signal, that modulating signal, actually have a different amplitude. Or we can check whether it has the same amplitude or a different amplitude. We can check it out. Now, if it has the same amplitude, that's not a problem. But if we change it, so that point will come ahead of that point. Look at this point and this point. Again, this point is greater than this point. So we will identify multiple points at multiple time intervals. Now, multiple points at multiple time intervals, the particular pulse level has been identified. Now what we need to do is, we need to identify, still it is an analog signal. Now we are actually checking out the pulses out there, but it is still an analog signal. Let me remind you, it is not digital signal yet. Now what we need to do is, we need to identify those quantization level. Now what is those quantization level? They are level, every voltage level or every amplitude level will be defined a particular quantization level. So if it is nearer to particular quantization level, that value of that particular signal and the pulse will remains to that point. So whatever is near, it will come to that point only. If this point is near to this point, it will come around this one, or if it is come nearer to this one, it will come like this. So we will have a different signal, different amplitude and discrete level. Now this voltage level and this difference level, this quantization difference level, will always be considered as delta V, and it will always be known as quantization level, and this difference is 2 MP divided by L. Now L are the intervals, total time intervals in that particular signal. Like in this 1, 2, 3, 4, 5, 6. 6 are there. Again 6 were there. So 6 here, 6 here. So 12 will be there. MP, if we decide that this is the maximum quantization limit of that particular signal, so it will be there. So we will determine how many levels will be there. So accuracy can be achieved by increasing L. If we are increasing that particular interval levels, so we will get the better quality and accuracy in the system. Now number of quantized levels are quite different. So if we choose more levels, we will have a better option to get the proper digital signal. Again, now this signal, now one thing is there, analog to digital converter. Analog to digital converter, when we say ADC, analog to digital converter, I am telling this term because this term is quite frequently used in examination as well as this particular circuit. Now this term is called ADC. Now when we say sampler, of course this will be done after going through sampling. We have already understood the sampling and the sampling frequency, how you are going to choose that, and by sampling theorem you will assign that this will be your particular frequency level by which you can actually make the sampling possible. Now sampler plus quantizer, this combination is called ADC, analog to digital converter, and the reverse, this is done at transmitter side. This operation is done at transmitter side, and the reverse operation is done at receiver side. So that is called DAC. that is digital to analog converter. So whenever in exam or in terms of terminologies, if they are asking you what is ADC or DEC, so ADC, analog to digital converter, is I beg your pardon, sampler and quantizer. Whenever sampler and quantizer terms has been used, you can use ADC, and the reverse is used for DEC. Now, how you are going to convert an analog signal and generate a pulse code modulated signal? What we need to do is, we need to have analog signal first. This is the modulating signal which needs to be converted into digital signal. Now this signal will pass through low pass filter where critical frequency is FM. By this frequency you will choose what kind of frequency spectrum or spectral components are needed to be sent. After this, what we need to use is sampler. Sampler is normally which we are using this circuit. Whenever we are talking about the normal PCM transmitter circuit, we use analog signal, LPF, sampler, quantizer, encoder, and output of the encoder is PCM. But in practical purpose, in practical utility, we are using analog signal, LPF, then sample and hold sampler. Sample and hold sampler will actually used in this particular circuit. Then the output of this one is actually passed through quantizer. These two devices, as we know, are ADC in combined. Now when we have the quantization levels determined and when we need to digitalize, now this is not a proper digital form signal. It is a digital signal, but we need to proper digital form signal, so that signal needs to be sent to digitizer, or we can say the encoder circuit. This encoder circuit will have V digits. By this we can actually identify those particular voltage levels, and now it basically is the digital signal. Now this needs to be sent to parallel to serial converter. This parallel to serial converter will make the sequence out of it, and the resultant signal is called PCM, that is pulse code modulated. Yeah, pulse, or we can say this is the pulse code modulation generation. Now this is how we are going to generate the signal. As we can see, the timer is there where sampling frequency is always taken as 2 FM. It is greater than or equals to 2 FM. Now why we take this 2 FM? As we have already understood that whenever we are taking this frequency below FM, 2 FM, there will be overlapping. There will be an overlapping of signals. So we don't want to do that. That is the reason we are using this sampling frequency in this timer, and this timer will be given input to two devices, sample and hold, and parallel to senior converter. This is how this circuit, this PCM generation has been done. If you have any query, if you have any questions, please ask me the questions in the comment section. You can ask me any type of questions regarding this input, how you are going to do this. Right now we can see this. This is the quantization output. After quantization, that particular output will be sent to encoder. The encoder, where we have multiple levels selected in the quantization, after this encoder will decide what is the value which needs to be sent, and that particular information will be encoded. And after parallel to serial converter, this will get the digital form of that particular analog signal. So at the receiver side, we are going to do the opposite thing. Now there is one problem in this particular system. What is that? The quantization error. There is a possibility that during the quantization, this particular problem is generated. Now how it is going to generate this? That whenever we are saying there is a minimum distortion and during this, after this quantization process, then this is called quantization error, and this output is considered as xq and ts. Now ts are sampling time, as we know, and are the number of levels where it is been defined, and q is denoted because after this quantization has been before during this is actually the thing that this is the quantization process has already done in this particular signal. So we have some form of digital signal. Now this some form of digital signal, when we send it to encoder, it will actually make the proper output. Now there are two kinds of quantizer being used in this. The first one is, the first quantizer which has been used is the uniform quantizer, and the other form which we have been using are non-uniform quantizer. Now uniform quantizer and non-uniform quantizer are different in terms of working and their processes. Now whenever we have this non-uniform quantizer, the peak value of that particular signal will be changed. Now how they are going to be changed? It can be understood by several examples, but we can see from one diagram by which it can be understood. Now uniform quantizer and non-uniform quantizer are the two types which has been done in any type of PCM generation method. Now how we are going to do that? Now suppose there is a particular signal which is already passed through sampler and LPF. First from LPF, low pass filter, and then from a quantizer. Now in the uniform quantizer, whenever we are saying is in the uniform quantizer, the label will be there. So what are those labels? Suppose this is the signal. Now again we are getting this signal. Now this is the maximum and this is the positive maximum, this is the negative maximum. It actually varies from 4 delta to minus 4 delta. This is how this quantization has happened, and multiple quantization levels have been achieved. Now we can see this. Now there is possibility of error in this. Now wherever there is a problem, how this problem occurs is, let's see this diagram first. Now this is 4 delta, this is minus 4 delta. Now maximum quantization error in this particular signal, maximum quantization error in this particular signal will be delta by 2. So this is the maximum which can be achieved. Now there are number of quantization levels out there. 4 delta, when we are saying it is a 4 delta, so it is denoting a particular signal. Suppose this is minus 4 delta and this is 4 delta. So maximum quantization error in the uniform quantizer will be delta by 2. How we are getting it? Now suppose this particular figure, as we can see that error in particular signal is x cube NTS minus x NTS. If you are talking about an error, so this is QE, quantization error here, and that level is delta by 2. How we are getting this is E is delta by 2 minus 0, that is delta by 2. Now this is the level, maximum level on which this error is occurring. So we can see what if we want to actually check the error. This quantization figure, the signal needs to be there, and original signal needs to be subtracted from it. So what we get is delta by 2. So that is the maximum quantization error. So we can say that this quantization error will occur in uniform quantizer. Now there is a possibility that we can use a better form where this quantization error is minimized, but this cannot be completely eradicated. So what we can get is the better signal. Now what will be the transmission bandwidth? Other part is the transmission bandwidth of PCM signal. Now whenever we are saying this, transmission bandwidth of PCM signal, whenever we are talking about it, now transmission bandwidth of PCM system. Now what will be the transmission bandwidth of this particular signal? Now whenever we want to calculate this, now if you are talking about the V number of binary digital signal, where we are getting this here V digits. Now Q will be, the quantization level will be 2 to the power V. Now here if you are talking about V equals to 4 bits, the number of quantization level are 2 to the power 4, that is 16 quantization levels are required. From this formula, each time whenever you get the number of bits you are getting after encoder V, then the number of quantization levels are 2 to the power Q to the power V, and that are, like suppose if you are talking about the 4-bit number, so 16 quarantine level will be there. Now each samples are converted to V binary bits, so number of bits per sample. So number of bits per sample are V, and number of samples are because this is the sampling frequency, so number of samples in that particular are, so number of bits per second are V into Fs, and VFS are called signaling rate of PCM. Now V into Fs, whenever we are talking about it, V into Fs are called the sampling rate. So sampling rate of, if in exam they are asking you what is the sampling rate of any PCM system, so that will be V into Fs. Here V are number of bits after encoder, how many digits are available, number of bits will be there, and fs is the sampling frequency, so number of samples per second. It will be denoted by this. Now signaling rate, it denoted by R, RV into fs, so bandwidth will be greater than equal to 1 by 2 R. So bandwidth is greater than 1 by 2 VFS. This is how you are going to get. So bandwidth will be greater than equals to 1 by 2 VFS. So put the value. Whenever we are saying Fs is greater than equals to 2 FM, just put the value over there. So bandwidth will be greater than equals to 1 by 2 into V into 2 FM. So bandwidth of any PCM system will be greater than equals to VFM. So any examination, if they are going to ask you about the sampling rate, the sampling rate will be equals to VFS and the bandwidth will be the greater than equals to VFM, or you can say VFS by 2. So by simply put, the bandwidth is greater than equals to, if you are just putting it over there, is equal to sampling rate by 2. So if you have the sampling rate in any system, you can say the bandwidth of the system will be greater than equals to sampling rate divided by 2. Just make it half and that will be your bandwidth. Now in the next topic, as we are going through it, we will talk about the PCM receiver and the quantization error in PCM receiver. So PCM receiver system will be the opposite of this PCM generation. So whenever we are talking about PCM receiver, this PCM receiver is the way we are going to convert the digital signal into analog signal, or the way the modulating signal will pass. So we will discuss it in the next chapter and next class. Till then, Bharat Mata ki Jai. Take care, stay in home and just follow the guidelines provided by the government. Good day.